Good afternoon, everyone. This is Sukanta De from Department of EC, University of Florida. Today, I will be discussing on machine learning for chip design. Chip design is the process where an integrated circuit is designed from its specification to the layout. This process is also known as VLSI design or electronic design automation. So today, basically discuss how machine learning can be applied to this electronic design automation flow. So this is the brief overview of my talk. Initially, I will describe history of hardware. Then I'll discuss what is EDA, its design challenges, how we can use machine learning for EDA, and different applications of machine learning in the domain of EDA, and what is our contribution. And then we will conclude the talk. So this is the first microprocessor manufactured by Intel. This is Intel 4004. It has the number of transistor 2300. So from there on, all transistor scaling is happening every year, and we are getting new transistors and a chip with better transistor count, with better efficiency or better power improvement, and various functionalities. So nowadays we are getting microprocessor or different chips with billions of transistors, even trillions of transistors. For example, like the Apple's A7 microprocessor, it has been manufactured in 2013, and it has like 1 billion transistors. Subsequently, for their other versions, like in Apple A10, the number of transistors was 3.3 billion, and it came in 2016. So the last year, the Apple's A16's bionic processor, the transistor count of that microprocessor was A16. The microprocessor count was like 16 billion. So with time, the transistor scaling is happening, mm, and the size reduces, cost per device reduces, performance increases. So I have like lots of slide in this talk, so I'll be skipping few slides. So I'll be skipping those which are not important. So this is the image of a Cerebrus wafer scale engine. This is a AI microprocessor basically, and it has like 1.2 trillion transistors, and this is manufactured using a whole wafer of the chip. And this is a like huge, it can process in high AI workload. And compared to the, if you compare the size of this wafer scale engine with a largest GPU, so like the largest GPU has like 21 billion transistors, and it is 1.2 trillion. And if you compare the size also by area, like in the largest GPU has a 815 micromillimeter square area, and it has like 46,000. So it's basically take a whole wafer space. And nowadays this transistor scaling is happening, that's why we are getting devices with more number of transistors, more number of functionality, more performance. But there are some challenges, design challenges, manufacturing challenges. And that's why like so in manufacturing challenges to a setting up a cheap manufacturing cheap fabrication facility is very costly. So in India only, we have only one experimental uh, fab like SCL Chandigarh, which produces some chips for the ISRO, and it uses like 180 nanometer setup, not the latest technology out. And currently the government of India is planning to set up different fabrication chip fabrication houses, because this is one of the important aspect with respect to the country's security. Because so in the government of India has set up like Indian Semiconductor Mission, and like Vedanta and Foxconn, they are proposing to set up a semiconductor fabrication facility in the Gujarat. So there are different with transistor scaling. There are various challenges in the design, in the fabrication, and so it has been a very difficult so far. We believe the machine learning can help this design process, and like we can explore the different challenges what machine learning has solved in the chip design process. So also this chip design or EDA plays a big role in the fabless industry. So there are various companies which which we consider as fabless. Basically what they do, they only design the chips, they don't manufacture the chips. They send design the chips and send it to some manufacturing house like TSMC. And example of these fabulous houses are like Nvidia, AMD. They are like totally fabulous. They only design the chips. So chip design is also an important aspect of this VLSI design and manufacturing process. So we today will be discussing about this chip design. So this chip design or electronic design automation is consists of two part. Like one is the circuit or logic design or functional design flow, and another is the like physical or the chip layout design. So the objective of this electronic design automation is to create the layout from the specification of the chip, so that in order to decrease the human effort in the design process and to automate and make the design cycle faster. So this to my talk, focus on my talk will be morely on the physical design aspect, how we can make different kinds of how we can solve different kinds of physical design problem using machine learning, that I'll be discussing. So this is not an important slide. So okay, so um, we have this net list, or okay, let me describe. So in the circuit design or the logic design step, for an analog we normally on for analog design or like custom design flow, start our design from a spice netlist. We design the design a circuit using a spice netlist, and then we create its menu, creates its layout, and then we get the like final layout of the chip. And so for this basically we use cadence, virtuoso, ADXL and layout XL to create the schematic and the subsequent layout of the design. Similarly for the digital design, we use hardware description language like Verilog or VHDL, and we create the initially the RTL level design, and then from there we do the synthesis to create the gate level design, and the subsequent from the gate level subsequent design we create the place and route, using automatic place and route tool we get the layout of the chip. So these are basically the two steps of the EDA. But what when is the challenge happens, and challenge is to design circuits with millions or billions of gates. That's why in the digital design we use like the HDL, because the digital designs are consist of large number of transistors, and we need lots of functionality. So also the challenge is to create the physical design from it. So once the functional design is ready, then to accommodate the design in a certain area is another challenge. And there are different different design challenges, layout design challenges we face. So let's discuss the chip design flow once, and then we'll discuss the physical design flow, and then I'll talk more about the challenges and machine learning aspects of this. How we can so normally a complete chip design is like we start from the specification, and then we do the architectural design. From there we get the create the RTL, and we do the logic synthesis. We get the physical design, and we do the verification, and after that fabrication, packaging, and test. So in the physical design, there are majorly three four important things like floor planning, placement, clock tree synthesis, and then the routing and the timing closure. So with these steps we get the so each of this in process is like a difficult one. Like in floor planning, we we decide where we will be placing different logic blocks of the circuit, and then find the placement stage, like final placement happens. Then we do the like how the clock is reaching to all of the blocks that we test and verify, and then we do the routing, and we do the timing analysis. So these are basically the three important steps in the physical design flow. So suppose this is a floor plan of a chip. So these are basically the functional blocks, and this yellow are like the pins of the chip, different pins of the chip. Now suppose we have this power pads around power pins like 1.8 volt power pin, and we are creating a metal grid or power grid, we say, to transfer the power from the power pad to these functional blocks. So what happens is during the power transfer, since these metal lines have some resistances, there are some voltage drop occurs, and these functional blocks do not get like whatever is it intended for it. So suppose for a large design, if there are number of functional blocks are more, and then it may happen like for a 1.8 at the pin voltage, we may be getting 1.5 volt, and then it might happen that these function blocks are not getting the voltage what it is designed for, and then this function block may malfunction. So that is one of the issue in this floor planning stage or this power grid design stage. So what we need to do, we have to initially like analyze this power grid, how much power is we are getting in at the different blocks. So for that, what we do, we take this only the power grid, we take the power grid, we make it as a like square grid, and we can take the its equivalent circuit. Like for now, we let's say only we are considering these metal lines have only the resistance and ignoring the inductive or capacitive effects. We get a grid like structure of resistors. Then for the functional blocks, we model it as a like current source, time varying current source, and then it becomes a simple circuit, and we can solve it using KCL and KVL. But the challenge is when the number of transistors is more or number of functional blocks are more, it will have like billions of nodes of, and solving this circuit using for the billion nodes is a huge task. So for that, we how on the opportunity is like how we can solve these billion nodes of circuits in a faster way to do the power grid analysis and to obtain the voltages, and how we can use machine learning. So I'll be discussing about this, and this is basically my work, and I'll be discussing about this, and later on have proposed some of the heuristic based approach or probabilistic based approach. So one issue I already discussed about this IR drop. So another issue happens is like when current passes through the electromigration. mm, when current passes through this metal interconnects, over a long period of time, it transfers momentum from the metal atom, from the electrons to the metal atom, and some of the metals get displaced, and some voids and halogs occurred like this. Here you can see one void has occurred, and like this here you can see some halog has occurred in the metal interconnects. So this basically reduces the lifetime of a chip or the reliability of the chip, and how we can reduce this two issue, that is one of the major task. So these two are basically the design challenges in the power grid. And designing power grid is one of the important or critical aspect of the physical design flow of a chip design. So since I have worked on these two phenomenon, so I'm more focusing on these two problems. So artificial intelligence has been there since 1950s. Initially, it meant like any machine which possesses some kind of intelligence or competition capability. We used to call it as artificial intelligence. Subsequently, from 1980, it's like support vector machine, which can classify like the two classes of data, two classes of data points. Then we used to know those kind of algorithm as machine learning, but it was not that famous. It was some other kind of numerical approach which can be used to solve some problems, because there was not much of data processing unit at that time. But with the advent of data processing unit like GPUs, we have the capability to process more data. Then this machine learning has been famous, and it had been come in a newer form as like the deep learning, with like various other additions like different deep neural networks and many other such kind of algorithms. So my work has been mostly on the supervised learning approach. So supervised learning is basically a label data for some kind of input features of some data set. We have some kind of label, and then from this label and input feature set, we generalize this and we make a model, and from there we try to create machine learning model and predict some kind of unseen data set. And that's how we do the machine learning or supervised learning. But why ML for EDA now? Because the designs are getting complex and large. Big data is associated with each design. So when we create a design, lots of data is generated. So we can use those data and create some meaningful information and create a machine learning model out of it. Time also, these design cycles take a huge amount of time and resources, like power also, including the manpower. Also, like the newer technology nodes evolve in every alternate year. So why not use the historical knowledge to create a machine learning model to generate some of the designs or some of the design solutions for the next technology node. That can be another motivation behind the machine learning for chip design. Also, so these are some of the reasons we believe machine learning can be a good alternative for over the traditional approaches in the chip design on ADA. So there has been different works in the literature for solving different EDA problems using machine learning. So today I'll be discussing mostly on my work, which is machine learning for like power grid design, and machine learning based for electromigration, our aging prediction. These two works basically, we have published this work, and I'll be discussing on these two works mostly. Uh, so this work is published in day 2020. So here we propose the machine learning for a model for power grid design for the first time. So what we did, so yeah, I already discussed about the machine learning, or I already discussed about the power grid design problem. So one is the airdrop issue, another is the electromigration issue. So we need to, while we design a chip, we need to take care of these two issues within some certain limit. So how this power grid planning process started, like initially some power grid lines and widths are planned accordingly. From those power grid design plans, we do some kind of extraction, and we can do power grid of modeling like RLC modeling or only resistive modeling. So from then we do this power grid analysis to find which areas are affected, which areas of the circuit is getting what voltage, and where the air drop is happening. Then we try to basically fix those air drops, and until unless this air drop is within the allowed limit, we just kind of iteratively keep on doing this power grid fixing. And when all the airdrop margins are within allowed limit, we say that we have the power grid design. We try to propose this approach using some historical data, and we propose the machine learning approach for that. So from some historical power grid design and data and specification, we do feature extraction. We do features extraction, and we created a training data set, and then we use this training data set to train a neural network. And for another new kind of power grid specification, we try to predict it, and we basically get the predicted power grid design. So what kind of features we have selected? So for that we have we have evaluated the r square score of the different power grid parameters. So when we say about the power grid, when we say about this power grid locations, so for a power grid metal line, we have like xy coordinate of the current locations or the currents of the function blocks where it is connected, and how much current that function block is drawing. We basically consider these two as our input features, and the width of the metal line on which the air drop mostly depends, that we consider as the output feature. And basically we have some other kind of features also, but we, after doing this feature extraction or like the feature analysis, we have found this combination of features works very well. From this figure, you can see that though for those features the r square score is near about 1, we consider that feature. So if we take only the x coordinate of the current source of the functional block, then the feature r square value is not good. R square values is good only for the combined features, and that's why we have considered this combined set of features using xy location and the id current drawing capability, value of the current drawing capability, and based on that we created the machine learning model. And so the problem formulation is like that: given an xy coordinate and id, then predict the metal width required which satisfy the ir and em margin, and given the given the width and the current drawing capability, then predict the ir drop. So we have like thousands of interconnect, power grid interconnect, and for each of the interconnect we try to solve this problem for our design. And the machine learning model we use is like 10 hidden layer. For the optimizer, adam optimizer we have used, and then then we use this data set to train a neural network, and we do the testing for some kind of new data sets with part type design, like whatever we used in the training, we part type those designs, and we considered that as a test set, and we tested our efficacy of the proposed machine learning approach. So that was the thing. And when we compared our proposed machine learning approach with the conventional approach, we got like around 5 or 6x speed up. So that's how we can say that machine learning approach can be useful for predicting the task. And if we see the like I drop quality what we get, it's like almost similar. The error is like around 2% error we have got. So we can say that machine learning can be good alternative for this kind of and this kind of airdrop prediction or power grid with prediction task. And like this is one of our work, and another work is machine learning for electromigration or aging prediction of the pg design. So fast, this is also one of the fast machine learning model we have proposed in the literature, and we have used similar kind of machine learning supervised learning approach. So existing models, so what we generally use, that is like the electromigration equation given by Black's. So Black's model is not that accurate, and it is also time consuming also. And there are other physics based model for the electromigration analysis, um, that those are physics based approach, those seems to be accurate. Those claims to be accurate, but those takes huge amount of time for for its convergence, like 14 to 16 hours. So those are not scalable for the whole power grid network. Those can be implemented for some kind of interconnect tree. So if we use our machine learning approach what we propose, and then I think we get a good trade-off between the accuracy and the convergence time. So our machine learning model is similar to what we proposed in our previous machine learning model. We created the training data set from the power grid specifications, and then we created a supervised modeling and supervised machine learning model, and then we tested it for some kind of test data set, and we get the electromigration aging. So similarly, we have used R square score for its evaluation. So here only the difference is the input features what we selected for the electromigration problem and the output features. So here the output feature we considered as the MTTF mean lifetime, and the input features are the current density, interconnect length, and the operating temperature and the IR drop as the input feature. By considering this dataset we created the model, and we created the model machine learning model, and we obtained the resulted MTTF, and this is basically our experimental flow. So you can see that this is also similar to the previous model. So, so here one of the difference you will get is here we have proposed a new failure criteria. After the prediction stage we create a failure criteria to improve the MTTF value, and then once we get the mean time to failure of this predicted power grid designs, there we do some kind of labeling which are more mortal or non-mortal, and from there we have created another logistic regression based classification model, and there from there we are getting which are the mortal interconnects, and then we can basically fix the design of these mortal interconnects, and to in order to increase the lifetime of the chip, or in order to make it in order to make the chip more reliable. So here also if we see our proposed developer achieves significant speed up over all of the state of the art algorithms when it was published. So after that, there are many other algorithms are coming, and the accuracy wise also our machine learning approach is closest to the accurate method of this 2016 which was published and better than all other state of the art methods. So in this way we can say that machine learning can be a good alternative for this electromigration averaging prediction. And there are lots of other works required to in this domain to. So machine learning for EDA is still a very very on its new stage, and we need more research in this domain to make this machine learning for EDA a mature domain. So we need more people, we need more human resources or researchers to carry forward this work, and try to solve different problems of EDA. There are many other problems. This here I have shown just two example of two problems of EDA, and there are many other problems which are unsolved. Even with the traditional approaches, there is no solution for some of the algorithms. So we can try to use machine learning for those problems. uh, so that's what I feel like. At the end, I want to say that machine learning can solve different EDL problems, and many researchers have already demonstrated that. And there are many unsolved problems in EDA which can also be solved. Uh, uh, so existing ML was not that mature, and so lots of R&D is required. And in future, the main goal of this machine learning for ADA is um, no human in loop, and automatically some machine are creating the layouts from its specification. So that is the final goal of this machine learning for ADA domain. So with that, I want to end this talk. And if you have any question, you can email me. And thank you.